All right, so 3.8 is about graphs of trigonometric functions. And I'm going to take a slightly different approach than you may have seen with the graphs of trig functions in the past. Most of the time, when you take a trig class and you talk about graphing trigonometric functions, you sort of go through these complicated steps where you find the period of the function, and then you divide it into four equal parts, and then you find the function values corresponding to each of those things, and it seems like this really sort of complicated process. And it's not that any of those things are bad. And in fact, when I teach trig, that's how I teach graphing trig functions. So there's nothing wrong with that. But what I wanted to do is give you a slightly different perspective. And I just want you to think of graphing trig functions like you would think of graphing any other kind of function. Okay, so you can take a parent function, and in this case, the sine function. This is what sine x looks like. This is the parent function, right? So it goes through 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. And so those are the 5 points that I would like for you to shift around. And so if we're confronted with something like sine x plus pi over 2 minus 1, then I just want you to treat this like you would treat any other transformation of any other kind of function. So that means that we're going to take our parent function, our sine function, and we're going to shift it to the left pi over 2 units, and we're going to shift it down 1 unit, right? And that's really all there is to it. I'm saying show at least one period. For those of you who are maybe not familiar with that terminology, a period of a trig function is just one repeat, right? So all of the trig functions, when you look at their graphs, they repeat over and over and over again. So I want you to show at least one period. You can show more than that if you like. Okay. So I'm going to be shifting left pi over 2 units. So instead of left pi over 2 and then down 1. So instead of having a point at 0, 0, I'm going to have a point at negative pi over 2, negative 1. Okay. So I'm just going to mark this negative pi over 2, negative 1. The next point, the next point, instead of being at pi over 2, 1, I'm going to subtract pi over 2, so I'm going to be at 0, 0. Right? So the next point is going to be at 0, 0. Instead of having a point at pi 0, I'm going to have a point at pi over 2, negative 1. Instead of having a point at 3 pi over 2, negative 1, let's see, 3 pi over 2 minus pi over 2 is 2 pi over 2, that's pi, right? So it's going to be at pi. And instead of being at negative 1, it's going to be at negative 2, right? And then finally, instead of having a point at 2 pi 0, I'm going to have a point at 2 pi minus pi over 2. That's 4 pi over 2 minus pi over 2, so that's 3 pi over 2. 3 pi over 2, and then instead of 0, negative 1, right? So I get this configuration of points. You'll notice that it's exactly the same configuration of points as the original sine function. It's just been shifted left pi over 2 and down 1. So there is one period of the sine function. And of course, this goes on in both directions, right? We should label the x-axis though. So I want you to definitely label the x-axis when you're doing this. So there's negative pi over 2, pi over 2, pi, and 3 pi over 2. And this is negative 1, negative 2. Okay, so that's what that one would look like. Okay. Let's do one for cosine. So cosine function looks a lot like the sine function, except that it has been, instead of starting at 0, 0, and then going to pi over 2, 1, and going like this, it starts at 0, 1, and then goes down to pi over 2, 0. But it's still the same kind of sinusoid, I guess you could say. If you take this graph and you shift it over to the right, pi over 2 units, then you get the sine function, right? Which, you know, gives you sort of the periodic identities for sine and cosine anyway, right? But you can see clearly that this is just the sine function, but it's been shifted left pi over 2 units. Anyway, so let's graph negative 2 cosine x plus 1. So what this is going to do is it's not going to shift, and by the way, it's not x plus 1 in parentheses, it's cosine x, right, plus 1 on the outside. So we're not going to be shifting left and right at all, but we will be multiplying by a factor of negative 2, multiplying the outputs by a factor of negative 2, and then adding 1 to them. So taking the point 0, 1, for example, we're not going to shift it left and right, so the x-coordinate is still going to be 0, but the y-coordinate is going to be multiplied by negative 2. 1 times negative 2 is negative 2, and then we're going to add 1. Negative 2 plus 1 is negative 1. So instead of 0, 1, we're going to have 0, negative 1 for our first point. Pi over 2 is 0. Pi over 2 is 0. Well, 0 times negative 2 is still 0, and 0 plus 1 is 1. So we're going to have pi over 2, 1. Pi, negative 1. So we're not going to shift left and right, so we're still going to have pi for our x-coordinate. For our y-coordinate, negative 1 times negative 2 is 2, and 2 plus 1 is 3. And then 3 pi over 2 is 0. Again, 0 times negative 2 is 0, plus 1 is 1, so we're back here. And then 2 pi, 1 times negative 2 is negative 2, negative 2 plus 1 is negative 1. So we get a picture that looks something like this for the cosine function. And of course, this goes on and on in both directions. Okay, labeling the x-axis, so this is pi over 2, pi, 3 pi over 2, and 2 pi. And this is negative 1, 1, 2, 3. Okay. Let's look at the tangent function. So the tangent function looks something like this. It's this repeated copy of this almost cubic looking curve, right? So it repeats over and over and over again, but it has these asymptotes at negative pi over 2 and at pi over 2, and then at every odd multiple of those. So like at 3 pi over 2, 5 pi over 2, 7 pi over 2, you're going to have asymptotes in all of those places, right? That's what I'm trying to describe here. So the x-intercepts are going to be on the integer multiples of pi, so like 0, pi, 2 pi. And then the asymptotes are going to be at the odd integer multiples of pi over 2. So at pi over 2, 3 pi over 2, 5 pi over 2, and so forth. So when you go to graph this function, one thing that kind of helps you, that might help you remember what the shape of the function is to remember that tangent is sine over cosine. So you're going to have an asymptote whenever cosine is 0, right? Because the function will be undefined there. So you're going to have an asymptote whenever cosine is 0. So if you can remember where cosine is 0, then you know where you have asymptotes on the tangent function. Meanwhile, you're going to have x-intercepts whenever sine is 0. So if you can remember where sine is 0, then you know where tangent is 0. Now the points that I want you to shift around when you're graphing the tangent function are these. And actually these two here are not really points at all, they're asymptotes, right? But you have an asymptote at negative pi over 2 and at pi over 2, and it's important to get those on the graph. Then in addition to that, you should shift around these 3 points. So let's practice doing that. So we'll graph tangent of x minus pi over 4. So we're going to be shifting to the right pi over 4 units, which means that instead of having an asymptote at negative pi over 2, negative pi over 2 plus pi over 4 would be negative pi over 4. So we're actually going to have an asymptote at pi over 4. Okay? So we have an asymptote at negative pi over 4. Okay, and then this point here is going to be shifted again right pi over 4 units. So we're going to add pi over 4 to the x coordinate here. Negative pi over 4 plus pi over 4 is, of course, 0. So we're going to have the point 0, negative 1 on the graph. Adding pi over 4 to the x coordinate here, we're going to have pi over 4, 0. So pi over 4, 0 is on the graph. And then adding pi over 4 here, we're going to have pi over 4 plus pi over 4 is 2 pi over 4. That's pi over 2, right? So 2 pi over 4. 1. And then finally, pi over 2 plus pi over 4. That's 2 pi over 4 plus pi. That's 3 pi over 4. So pi over 4, 2 pi over 4, 3 pi over 4. And that's where we have our other asymptote. Okay, and now you just connect the dots with a curve that looks like the tangent function. Okay, something like that. So we've got 1, negative 1, pi over 4, pi over 2, and 3 pi over 4. And here we've got negative pi over 4, of course. This thing, it should go without saying, is going to repeat over and over and over again. But as long as you get one period on there, I'm happy. Okay, so that's what the tangent function looks like. Cotangent function is really similar looking. It's going to be decreasing. So whereas the tangent function kind of increased from left to right, the cotangent function decreases from left to right. And that should make sense because cotangent is the reciprocal of tangent, right? So, so it's decreasing. The other thing about it is that the asymptotes and the x-intercepts are in different places. In fact, they swap places with the asymptotes and x-intercepts on the tangent function. And that's because cotangent is cosine over sine. So now you're going to have asymptotes whenever sine is 0 and x-intercepts whenever cosine is 0. Okay? So for the cotangent function, you know, you're going to have an asymptote whenever sine is 0. So you're going to have an asymptote at 0 and at pi, right? So you're going to have asymptotes at 0 and at pi. And then in between those asymptotes, I want you to shift around these 3 points. So let's practice doing that. Okay. So in this function here, again, if I wanted to say cotangent of x minus 3, well then I would put it in parentheses, right? But that's not what we have here. We have cotangent of x and then minus 3. So what that tells me is that we're not going to be doing any shifting left and right. We're just going to be shifting down 3 units. So the vertical asymptote that I should have here at 0 is still going to be a vertical asymptote at x equals 0, right? You shift this vertical asymptote down 3 units, it's still a vertical asymptote at 0. Kind of hard to mark it on the graph. Okay. Next point is pi over 4, 1, but we're going to shift it down 3, so 1 minus 3 is negative 2. Then we have pi over 2, 0. That's going to go down 3. Then we have 3 pi over 4, negative 1. We're going to shift it down 3, so we're going to end up at negative 4. And then finally, by the time we get to pi, we've got another asymptote. And shifting that asymptote down 3 units, it's still a vertical asymptote. Okay? So now you connect the dots with something that looks like a cotangent function. And there you go. So that's that one, right? We should label all these things. We've got pi over 4, pi over 2, 3 pi over 4, and pi. Okay? So that's what that one looks like. And again, you know, of course, this thing is going to repeat over and over again, but that's the idea. That was really poorly done. but there you go. Okay, so there's cotangent. Last two functions, the secant and cosecant. These things are also pretty well understood if you think about them through the lens of their reciprocal functions, right? So secant is really 1 over cosine, which tells you that, again, you're going to have asymptotes whenever cosine is 0. Okay? Excuse me. You're going to have asymptotes whenever cosine is 0, and secant is going to be 1 whenever cosine is 1. Okay? It's going to be -1 whenever cosine is -1. So you get this kind of graph that results when you graph the secant function. What I want to point out to you is this. So if you were to graph the cosine function over the top of the secant function, remember that cosine starts at 0, 1, and then it goes down to pi over 2, 0, and pi -1, like this. And of course it continues in both directions. So this is what the cosine function looks like. Right? So what you'll notice is that, again, whenever cosine is 0, now you have an asymptote. Right? Asymptote, asymptote. Whenever cosine is 1, secant is 1. And whenever cosine is -1, secant is -1. So if you can graph, if you're confronted with a situation like this, negative secant x minus 2, if you'll just graph negative cosine x minus 2, then the secant function will just be, in some sense, it's like the opposite of whatever you get when you graph the cosine function. Okay, so that's one approach to graphing secant and cosecant functions. Secant is 1 over cosine, cosecant is 1 over sine. I'm just going to show you the transformation sort of idea. So you'll notice now that you've got asymptotes at negative pi over 2, at positive pi over 2, and at 3 pi over 2. So I want to get those 3 asymptotes on there. And then I need to get at least one copy of the almost parabola-looking thing that's pointing up and one copy of it pointing down in order to get one complete period. That's why I need these 3 asymptotes, right? But I want to get a copy going up and a copy going down. The copy going up is going to be this one here, and the copy going down is going to be that one there. So let's practice shifting these around. So here we want to graph f of x equals negative secant x minus 2. Okay, so I'm going to take my asymptotes. And again, this is negative secant of x minus 2. So I'm not shifting left and right at all. I'm only going to be multiplying the y-coordinates by -1 and then subtracting 2. That's not going to change any of my asymptotes, right? There's still going to be asymptotes at the same locations. So I'm just going to go ahead and put those on there now. I've got an asymptote at negative pi over 2, at pi over 2, and then at 3 pi over 2. So here, here, and here. Now for the other 2 points, right? 0, 1. First, I'm going to multiply the y-coordinate by -1, so I get -1. Then I subtract 2, so I get -3. So I have that 0, -3. And then for pi, -1, multiplying by -1, I get +1. And then subtracting 2, I get -1. Okay, so this is the scenario that I'm left with. Now, you should have some sense for what the secant function looks like. I asked you in the introduction to this chapter to memorize what the trig functions look like. So you should know that there's a gap between the parabola that opens up and the parabola that opens down. They don't overlap. So it wouldn't make sense, for example, to draw this one pointing down and this one pointing up, because then you'd have this space in between that's overlapping, and we know that the secant function doesn't look like that. What you should have instead is this one pointing down and this one pointing up. And that makes sense because of this negative sign here, right? We've flipped over the secant function. So even though the one that's opening up is usually on the left and the one that's opening down is usually on the right, if you flip that over, then you're going to get the one opening down on the left and the one opening up on the right. And that's exactly the scenario that we have here, right? So this is the picture you should get. Okay. And of course, this thing is going to repeat over and over again, right? Whoop. This on and on and on forever in both directions. So, so that's that, right? There's the secant function. One more example. Let's graph a cosecant. So, very similar looking graph, okay? Just remember cosecant is 1 over sine. So just like we did with the secant function, we can think of this like it's just the opposite of a sine function, right? Sine starts at 0, 0, and then goes up there, comes down here, goes back down there, and then it would come back up. But we're off the page. Anyway, but it extends that way in both directions. So if you were to graph the sine function, like if you were to graph 2 times sine of x plus pi over 2, then you would get then 2 times cosecant of x plus pi over 2 is going to be that same thing, but just in some sense sort of the opposite. Like whenever you have 0, you can have asymptotes, right? Whenever sine is 1, cosecant is 1. Whenever sine is -1, cosecant is -1. Okay. So again, if I want to get a full period of this graph, then I need to have 3 asymptotes, and then I need 1 copy of the parabola opening down and 1 copy of it opening up. And that's what you're going to get if you shift around these 5 points, but they're not really points, right? Some of them, these 3 are really asymptotes. Well, let's practice doing that. So here on part 6, I'm going to be shifting left pi over 2 units, and then I'm going to be stretching by a factor of 2. So I'm going to subtract pi over 2 from all the x coordinates, and then I'm going to multiply all of the y coordinates by 2. So let's see what that does to the asymptotes first and foremost, right? So this asymptote's at negative pi, but I'm going to shift it left pi over 2 units, so it's really going to end up at negative 3 pi over 2. I'm just going to go in increments of pi over 2. So if I have pi over 2, negative 2 pi over 2, and then negative 3 pi over 2 would be right there. So there's one asymptote. I usually I have another asymptote at 0, but again it's going to be shifted left pi over 2 units. So there's another asymptote. And then I usually have another asymptote at pi, but again, shifting it left pi over 2 units, it's going to be an asymptote at pi over 2. Okay. Now, as for these other 2 points, so negative pi over 2, negative 1. First, I'm going to subtract pi over 2 from the x coordinate. Negative pi over 2 minus pi over 2 is negative pi. That puts me right here. And then I'm going to multiply the y coordinate by 2, right? So negative 1 times 2 is negative 2. So that's where that point lands. This point, I'm going to subtract pi over 2. Pi over 2 minus pi over 2 is 0. And then I'm going to multiply the y coordinate by 2. 1 times 2 is 2. Okay, so this is the scenario that I end up with, and so it becomes pretty clear that the graph should look something like that. Okay, so I can label all this, of course, right? Negative pi over 2, negative pi, negative 3 pi over 2, and of course pi over 2 over here, negative 2, negative 1, 1, 2, and that's that. So that's my approach to graphing trig functions, at least in a pre-calculus / calculus setting. Most of the time in calculus, when you're in calculus, you're not going to ever sit down and graph in detail what a trig function looks like. It's more important that you understand sort of the basic shape of the function and transformations, which is why I want you to kind of practice what I've talked about in this section. However, there are a couple of things on the course outline that I have to cover in order to cover all of the topics in pre-calculus. So, so I do need to at least briefly mention amplitude and phase shifts because they're on the course outline. The amplitude of a function is half of the difference between its maximum and minimum value. Not all functions have an amplitude because not all functions have a maximum or minimum value. So looking at the trig functions, for example, the secant, cosecant, tangent, and cotangent functions do not have an amplitude to speak of, but the sine and cosine functions do. So for example, the maximum of 2 sine x minus 1 is, well, I know that sine x, the maximum of sine x is 1, so the maximum of 2 sine x minus 1 is going to be 2 times 1, which is 2, minus 1, which is 1. So the maximum is going to be 1. The minimum, well, the minimum of sine x is negative 1. 2 times negative 1 is negative 2, minus 1 is negative 3, so the minimum is negative 3. Thus, the amplitude of 2 sine x minus 1 is half of the distance between negative 3 and 1, right? So 1 minus negative 3. That's 1 half times 4, which is 2. Now, what you'll notice is that this is the same thing as that, and that's not a coincidence. In general, the amplitude of f of x equals a sine x or f of x equals a cosine x is the absolute value of a. So if we had like a negative 2 sine x minus 1, the amplitude would still be positive 2. Okay. So that's how amplitude works. You'll have a couple homework questions asking you what's the amplitude of this function. Okay. And then phase shifting is just another way to say horizontal shifting. Right? The horizontal shifting in trig functions is referred to as a phase shift. I'm not sure why we give it a special name, but there you have it. Right? So for f of x equals tangent x minus pi over 6 plus 2, this function would be said to have a phase shift of pi over 6 units, right? It's the horizontal shift. And that's all I have to say about that. However, I do want to discuss a connection now between the transcendental functions that we have been talking about in this chapter. So the last several sections have all been about trig functions. But remember, the first 3 sections of chapter 3 were about exponential and logarithmic functions. And so I want to show you how the exponential function e to the x is related to the trigonometric functions sine x and cosine x. And I think that this is really pretty interesting. So it turns out that the transcendental functions that we've covered in this chapter can be written as infinite polynomials. E to the x can be rewritten as this infinite polynomial. 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 and so forth. And there is a pattern with these numbers here that you're going to explore in detail in calculus. For those of you who are maybe familiar with factorials, right, this is 2 factorial, 3 factorial, 4 factorial, 5 factorial, and so forth. Cosine x can be rewritten as this infinite polynomial. Okay, which you'll notice borrows some of the terms from e to the x, but only the even ones. and it also alternates the sign. Meanwhile, the sine function can be rewritten as this infinite polynomial, which also borrows its terms from e to the x, right? But only the odd terms. And it also alternates signs. So it's really kind of an interesting thing, but we can convince ourselves of this by taking a look at some of these graphs in Desmos. So I think I'm going to stop the video here, and I'm going to pull up some of these things in Desmos so that we can take a look at them together, and then I'll post a separate video about all of this.